Imagine taking one of the absolute nastiest radioactive waste products of the nuclear age, literally dropping it to the bottom of the ocean, and using it to power a network of autonomous drone submarines, right? It sounds exactly like the plot of some sci-fi thriller. But here's the thing, this isn't a movie script. It's a real project happening right now. Welcome to today's Explainer, where we're going to break down exactly how the US is actively building nuclear-powered seabed batteries to solve a massive military logistics nightmare.
Okay, let's jump right in. 28.8 years. That is the exact half-life of a radioactive isotope called strontium-90. And when you think about what that actually means in practical terms, it's staggering. We're talking about nearly 3 full decades of continuous underwater heat and power. No cables running back to shore, no support ships bobbing on the surface trying to swap out batteries or refuel, just a silent, uninterrupted power source operating in the crushing, pitch-black depths of the ocean for practically an entire generation.
Section 1. Solving the drone power problem.
So why exactly did the Department of Defense kick off a program called DEPTHS, which, by the way, stands for Distributed Energy Provided Throughout the Seas, and award a $7.5 million contract to a startup named Zeno Power? Well, it all comes down to the unforgiving arithmetic of underwater robotics. You see, every single autonomous machine, sensor, or drone sitting on the seafloor is heavily constrained by its battery life. From the exact moment it drops into the water, it's essentially born with a ticking timer. And right now, the workarounds are honestly incredibly expensive and pretty inefficient. For example, the pressure-tolerant battery packs going into modern drone submarines, they only buy endurance by totally getting rid of the heavy protective housings, not by actually adding more energy capacity. They basically just cast the battery cells into polymer and drop them into water that exerts thousands of pounds of pressure per square inch.
The strategic stakes here are just incredibly high. As Admiral John M. Richardson, the retired former Chief of Naval Operations, put it, ubiquitous access to power in maritime environments is critical to maintaining U.S. leadership. Looking at this from an impartial geopolitical perspective, having a permanent power node fundamentally changes what a military can leave on the seafloor. And this is highly relevant right now because reports indicate China is concurrently working to wire the Pacific Ocean floor with its own networks of sensors. If you have an underwater charging station, it means your sensors can listen for months and your drones can operate indefinitely without ever needing to surface. That is a massive shift.
Section 2. A decades-old nuclear blueprint. Now, it might actually shock you to learn that this highly futuristic sci-fi concept, it's really not new at all. The underlying blueprint for this technology has literally been sitting in a Department of Energy archive since 1961. Yeah, we've tried this before, and understanding why it failed back then really helps explain why it just might work today. Take a look at the sheer scale of the historical contrast here. Under a 1961 program, the Atomic Energy Commission built the SNAP-7A. This was a strontium-90 thermoelectrode generator meant for a Coast Guard light buoy in Baltimore, Maryland. It used 4 capsules holding 40,800 curies of radioactive material. But here was the fatal flaw. Strontium-90 requires heavy shielding. I mean, very heavy. Those old marine units weighed thousands of pounds just to squeeze out a meager 5-watt electrical system. It was massively heavy, incredibly inefficient, and they ultimately abandoned it. Today's modern DEPTHS program, on the other hand, is completely flipping the script. They're aiming for decentralized seabed nodes that prioritize high specific power. That means they want significantly more thermal watts per kilogram than the incredibly bulky hardware of the 1960s.
Section 3. Strontium-90 meets Stirling engines.
So you're probably wondering, how exactly are they overcoming the hurdles that killed this project 60 years ago? Well, it comes down to 2 major innovations. And it starts with the notorious fuel source itself. Strontium-90 has a terrible reputation, and quite frankly, it's earned every bit of it. It's a highly dangerous radioactive fission product that turns up in spent nuclear fuel and at cleanup sites. Crucially, if it gets inside the human body, it acts just like calcium and heads straight for your bones. Keeping this stuff safely contained and just sitting still has been a ridiculously expensive line item on the Department of Energy's books for decades. But now, the government is basically turning a massive waste liability into a strategic asset. Zeno Power isn't out there buying fresh strontium. Instead, they partnered up in January 2024 to recycle a legacy radioisotope power system known as the BURP 500, which has literally just been sitting in storage at the Oak Ridge facility, gathering dust.
Okay, so the absolute crucial part here is how this dangerous waste actually becomes electricity. Let's walk through the mechanics.
Step 1, as the strontium-90 naturally decays into yttrium-90, it continuously throws off intense heat. That's just the physics part, and the best part is it requires zero maintenance. The real engineering breakthrough is Step 2. Instead of using a conventional thermoelectric generator, which remember, back in the 60s only converted a pretty terrible 5% of that heat into electricity, the modern system uses a Stirling engine. A Stirling engine is a closed-cycle piston engine driven entirely by a temperature difference. This one change drastically improves the conversion rate, meaning it can efficiently generate the actual electricity needed for these underwater submarine charging stations. It's brilliant.
Now, I should definitely note that Zeno Power's Stirling engine method isn't the only horse in this race. The Defense Advanced Research Projects Agency, better known as DARPA, has this program called RADS to Watts, and they recently awarded a $3.37 million parallel track to a group called Project Omega. While Zeno relies on heat to physically drive mechanical pistons, Project Omega skips the heat completely. They're actually testing a method that layers a solid isotope directly against a semiconductor to turn radiation directly into electricity. So it's a completely heat-free, piston-free alternative, basically just making a different bet on the exact same stream of nuclear waste.
Section 4. The ticking clock to 2027.
Whether we're talking about Stirling engines or semiconductors, this technology is moving out of the lab at an absolute breakneck pace. But the entire industry is currently staring down a massive physical bottleneck and a very real ticking clock to deliver. Because the biggest hurdle to mass producing these nuclear seabed batteries isn't really the design anymore, it's the manufacturing environment. You can't just build these things on a standard factory assembly line. You need what are called hot cells. These are heavily shielded rooms where technicians have to handle the radioactive material entirely remotely, peering through thick leaded glass and operating these giant mechanical arms. And there are very few of these facilities left in the United States. This project stopped being purely theoretical in June 2026 when Zeno Power announced a lease to restore the hot cell complex at the historic 1,600-acre Vallecito Nuclear Center out in California. Taking physical possession of those hot cells, that crossed the line from a defense contract on paper to a very real weapon system entering production.
When you look at the timeline, you can really see how aggressively this production race is escalating. We go from the initial DoD depths contract in late 2023 straight into securing the legacy radioactive fuel from Oak Ridge in early 2024. Then, they make the major leap of leasing the Vallecito hot cells in mid-2026. All of this rapid capital and huge infrastructure mobilization is aimed squarely at one highly ambitious deadline, delivering the first working units to government customers in 2027, with volume production slated for 2028. They are moving incredibly fast.
But that brings us to our final and maybe most critical question. The original plan laid out by Zeno Power included a fueled, full-scale demonstration in 2026. Basically, a tank-based test to prove the whole system works before it ever even touches the real seabed. But as of August 2026, no such fueled demonstration has been announced. The company notes they've tested the heat source and electrically heated power systems, sure, but that is a very different milestone than running a fully fueled, highly radioactive unit. With less than 5 months left in the year, the pressure is totally on. Will they pull off this full-scale demonstration in time? Or will the promise of a permanent 30-year seabed battery slip out of reach just as the Navy needs it most? It's a high-stakes engineering race for the bottom of the ocean, and we will absolutely be watching closely to see what happens next.